So last talk of this session, this is going to be slightly different, right? These are two members of the Fetch.AI team of recent ICO fame. I don't know if you heard about them. They're fantastic. Their white paper is fantastic. The stage is yours.
Thank you. Good morning. I'm Marcin Abram, and together with Daniel Honerkamp, we are going to present a consensus model that we develop at Fetch, which minimize agency of the leaders, and we will describe why we believe it's important. First, I will start from the motivation of that work. So in most of the blockchain, in proof of work, proof of stake, in other, usually miners are competing somehow to win a one-shot monopoly over the right to produce or propose new block. And when they have that monopoly in that round, they can usually select some transactions from memory pool, or they can, and specifically they can censor some transactions. They may decide to not include some transactions, or they can also add ad hoc new transactions, dummy transactions, for example, between sending money between two addresses they control. They can also, for example, in Ethereum, in other blockchains, they can reorganize the order of the transactions within one block, which might be might have some influence, especially if the transactions are interacting with the same smart contract. We should also keep in mind that usually in the blockchain where we have free entry and anonymity, we have the miners are engaged in competition that is repeated every round. And in order to incentivize them to follow a protocol, the reward must be bigger than potential profits from misbehaving. And also let's keep in mind that because the rounds are pretty much independent, we have to provide that incentive each round. So the miners have a static incentive to behave good or follow the protocol. And also in a long run, most of the blockchains with capped number of coins, the security is going to be based on fees. So it's need to think about ways of extracting the fee efficiently. And then nowadays, in most of the blockchains, we are using a generalized first price auction. And this has potentially a lot of problems because when the congestion is very low, the senders are not really, they do not have incentive to propose any significant fee. Because while even the miners have incentive to include any transaction with non-zero fee when the congestion is low, and therefore people are proposing very small fee, and it's very hard to actually extract any meaningful sum of money in such way. From the other point of view, when we are reaching capacity of the block, not even like let's even assume that in the average we can process all the congestion, that we don't have any transaction, that we don't have any queue. But when we are reaching the capacity of the block, then the senders are engaged in severe competition over the priority which transaction is going to be included, then the fees is going up very rapidly, and also senders are suffer because they are exposed to costly delays. Only the delays are motivating them to actually propose large fee. There are other ways of extracting fee. One of the many ideas is, for example, to use decade order auction, where where we have still fixed block, but now we are saying that everybody is paying fee equal to the lowest fee from the transactions that are included. So in this example, for example, we have size 4 of the block. We have some transaction with large fee, with small fee proposed. Everybody's paying free. However, there's a problem because then if a leader can ad hoc add some transactions or choose whatever transactions he or she wish, by including some dummy transactions with a high fee, we can make it seems like the competition is larger, and therefore everybody is paying more. This can be solved by limiting ability to add the dummy transactions or by distributing the reward from the leader. Another, yet just to show and highlight that there are other ideas, is, for example, monopolistic order auction, where we are adjusting the block. It has much better properties, but still there is a small margin where leader can, adding dummy transactions, manipulate the fee that everybody is paying. In the second part, we would like to go deeper and describe other problems or instability of the blockchain when the leader has a large power. Floor is yours.
Thank you, Marcin. So yeah, this will be a second strand of argumentation why we might want to limit the power of the leader. So this is from the same paper as our predecessor already talked about, from Carsten et al. And they introduced these undercutting attacks in the same paper. Again, this assumes a world where most part of the rewards come from fees and not from newly minted tokens. In this case, the miners might no longer be incentivized to build upon the longest chain. Instead, they might want to deviate. So imagine a scenario where we have an existing chain. The last block included transactions, most of the transactions with fees in the value of 500 tokens, and there are only transactions with fees of 20 tokens left. So you could either extend this chain, follow the protocol as it was intended, build your block with fees of 20 tokens, or you deviate. You don't build upon this block, but you fork it. You build a new block in the same height and include fees with transactions with fees in a value of 207 tokens in this example. And you purposely leave out a significant amount of tokens. Why would you do that? Because you want the next miner that will follow you to also build upon your block. So you end up in this equilibrium where everybody purposefully leaves out transactions to incentivize the next miner to build upon their block. So we are still for some time away for transaction fees to become the most important source, but even today there are issues with this. And there's a very recent paper from last month, and they very empirically showed that there exist these order optimization fees, which are essentially a direct profit from the control over ordering transactions. These arise from decentralized exchanges that rely on constant arbitrage to provide market prices. This constant arbitrage means that together with smart contracts, you can execute. Smart contracts simply mean you can make sure that you execute two sides of a trade within a block or none of them. And these arbitrage opportunities are basically what they end up doing is putting a larger price tag on these other undercutting attacks. Now, if the block in front of you, if you win the monopoly, the block in front of you included these big opportunities with a large revenue, you have an even larger incentive to fork this block and to reap these fees yourself. And they estimate these opportunities to already exist with the fee structure in Ethereum today. Now, how does this fit in with the agency of the leader? We want to either reduce the control that the leader has for including transactions himself, or we can simply mitigate these incentives or even remove them so that the people become indifferent of forking the last block or the last Q blocks by sharing the rewards across these blocks. Which seems like a very simple solution. There's one issue. This is not incentive compatible with a powerful leader. To see this, imagine a user who sends a transaction to a network with a fee f. And we have a block producer. He includes this transaction because he likes the fee. He gets a fee f. In this case, x is 1. He gets all the shares from blocks. But if we want to share fees across blocks to prevent these undercutting attacks, we need to set q smaller or even to a half. We might also want to share transactions across functions within rounds in other scenarios. But this opens the platform for third channel payments. Now, instead of sending the transaction with a fee f to the network, the sender can collude with the block producer and send it with a minimal fee epsilon. The block producer has all the power to include this transaction if he wants to, and he will get his share of that epsilon. At the same time, the sender can can make a third channel payment to a block producer, and they can share the difference of what's not paid to third parties, so that both are better off. And the important column is the other participants. If you're honestly following on-chain sending, other participants in the consensus will receive a share 1 minus x times the fee. But if you use these third channel transactions, they will only receive 1 minus x times this minimum fee, and everything else is distributed between sender and block producer. And this brings us back to limiting the power of the leader to choose these transactions, even if they are sent with only the minimum fee in the network. And this brings us to our contribution, to our consensus model at Fetch, which I will give the word back to Marcin for.
Thank you. Therefore, we are thinking about the ways how to design a consensus in such a way that the power of the leader is going to be limited. And we constructed the high-level overview. We have some elements where we have a random beacon. We can select random number, then we can use to select a committee. We are using DAC as a temporary storage or memory pool to keep track which transactions are arriving. But still, we are constructing block that can be notarized by other participants. And it's a proof-of-stake system where we have n stakers. Everybody is creating the same stake. We have epochs. In each epoch, we can evaluate the stake. People can exchange keys. They can construct global key by submitting shares. And this can be used to produce a random number every round. This random number can be used to determine a new committee and also to rank the committee. Another part is that using a threshold signatures, participants can endorse certain proposals, and when they are meeting the threshold, by gathering the partial signatures, if you gather enough of them, you can actually sign a certain proposal or block or whatever message, and this can be used as confirmation that enough people endorsed a certain proposal or are aware of certain proposal. We are using directed acyclic graph as a data structure to construct a common memory pool. How it works, people are submitting transactions that are linked to previous transactions, and really the consensus is about choosing a tip of that structure. So if somebody is, for example, somebody is proposing a tip, and then if we can reach consensus that yes, everybody agree that this tip was seen and everybody think that this tip is good, then we kind of reach an agreement also which transactions everybody already observed. this has also nice properties because when we are talking which tip should be selected, we can submit only the tip, not the entire data structure, so the communication cost is much lower. Technically speaking, when we to highlight the way how people are going to agree on the tip, they are using a threshold signature scheme where they are sending a partial signatures to of a certain tip, and if enough people are submit that signature, then the tip can be signed, and then by observing that the tip is signed, people know that enough people have seen other transactions. Where is the blockchain in that entire picture? When we are reaching consensus over which tip should be selected, then we are sure that majority of people already seen other transactions that are behind that tip, and therefore everybody will have immediately understanding how the block is going to look like. The entire data structure like this, the vertices with transactions doesn't have to live forever. It can be a temporary data structure where after a while we can disregard the tips that are old, because what we really keep at the end, there are the blocks. So more, because people have access to that shared memory pool of all the transactions, and we are sure that everybody sees exactly the same set of transactions, we can construct certain mapping of the transactions to the block. And here we can execute, or we can use certain auction mechanism to select, like when people can reach agreement which transaction they see, then we can say, well, we are going to use that or another function or auction that is going to select the transactions to the block. And also, because we have access to a random number, we can rank or create order of the transactions within the block. So we have the properties that we have a certain order of the transactions that cannot be directly influenced by the leader. So leader is choosing, leader. The members of the committee are ranked and they are submitting some proposal of the tip, but they have a very limited possibility to precisely tamper with the order. Those to conclude, because we would like to leave some few minutes for questions. We described some problems related to the fact that leader has one-shot monopoly, problem with the fact that they can choose transactions or change the order of the transaction within the block. And we are proposing a consensus that in which the power or agency of the leader is going to be limited.
Thank you. Quentin, since there's an IOTA evident part in this talk, I'm sure you have a question. No? So, I have a question about the IOTA part. So you have this DAG. How do you actually reach consensus on the DAG itself?
The trick is such that because we have random number, we can rank members of the committee. So we have all the stakeholders. We can, using random number, we can select certain subset of people. Then using a random number, we can also we can rank them randomly, where the random number is going to be a seat. And now the people from the committee with the highest rank, the proposal is going to be counted as more. So instead of like in the Bitcoin, for example, like people are rushing to be first. So the consensus about selecting, about limiting your possibility to submit your block, and basically we are saying the first is better, but because of the lags in the network, it may happen that you have two proposals, and then you have to wait a long time to select which chain actually is the best. Here, because you have actually a rank of the people, you know which proposal is best. Though, if you are selecting a tip that is pathological, or you are not going to cover all the transactions, you are trying to cover a very small part of the available transactions, it can be detected, measured, and another proposal from another high-ranked committee can win, and this can be algorithmic. It's not, I mean, depending on the design, it can actually be in the protocol.
So the winning tip is a mixture of the rank of the person who's saying it's a good one and of its actual IOTA type of weight.
Yes.
Is that right?
Yes.
Okay.
Yeah, maybe also importantly, the weight is, so each vertex is a collection of transactions. Sorry, each vertex is a collection of transactions, and because each vertex is associated with a staker, the weight is the stake. And because all stakes are identical, this becomes equivalent to maximizing the number of vertices covered. So it is, you have to maximize the stake associated with the vertices you covered, which is similar to voting.
And I would also add that additionally, because every member of the committee is kind of obligated to submit one vertex with the list of transactions, we can see if somebody is adding the vertex in a pathological way, and because they are staking something in that particular epoch, there is potentially a possibility to also enforce a good behavior. So either by sharing the rewards, we can incentivize them to produce a compact DAG, or we can say that because it will be visible that they are misbehaving and they are staking, we will have a possibility to kind of punish the people who are deviating from the protocol.
All right, I think we're good. We're going to have a coffee break, a well-deserved one. Thank you.